But you can just shut down the whole process and then have it restart later on. That's one strategy. I didn't say it was a good one, but it is a strategy, right? You don't agree it's a strategy? Yeah, well, okay, I got one yes, you're saved. Okay, so in a deadlock situation, we can just take this to the nth extreme, right? We detected a deadlock. Let's kill all processes. They all got into this mess. Let's just kill them all. And then they can just go restart whenever, right? And they can then go right back into deadlock again. You can kill them all again, then they go right back into deadlock again. Right? That's not a good strategy, but it works, kind of, sort of. Okay? The other is that you can do checkpoints. Right? So at some intervals of time, you just checkpoint each of your processes. And then if a deadlock does occur, then you just back these processes up to a previous deadlock, where it's a previous known good deadlock-free state, sorry. So you just back them up to a checkpoint, and then select a different one to run next time. Right? Then maybe you will avoid deadlock that way, or won't get into deadlock that way. It's kind of chance though, isn't it? Maybe, kind of. Cross our fingers. Do we like crossing our fingers in code that's going to be running an operating system zillions of times a second? No. So that's not a good method either. Or we just clobber them all again. Somebody just loves clobbering processes, I can see. So yeah, that's not a good strategy either, because as we just saw, it's chance. It's not a good way to build a scientific machine here. Okay, another way we can do it is just start one at a time, picking them off. Kill one, kill two, kill three. Oh, it's no longer deadlock, we're good. Okay, then ignore the rest of the problem. Right? Maybe it won't happen again. Oh, there's that chance thing again, right? All right, so that's got problems. The other way is I could just start preempting the resources, right? Halt a process, grab its resource, turn it in. I could do that, then those processes I'm picking on one at a time are having issues, and I could end up back in deadlock again if they're in loops and they run the same logic over again, going for the same resources again. I may be doing a lot of preemption. It's a lot of heavy work. It doesn't really help us. So recovering from deadlock is not a good, there really isn't a good solution here, is there? Another way you could do it is you can simply look and see, okay, how much time has this process been alive? Pick the youngest. You always go for the youngest, huh? Right? Go for the youngest. Or you can go for the one that has generated the least amount of data, using the least amount of resources. Well, that's not going to help you. You probably want to go for the resource-heavy ones, right? I would think that would be easier to, or far more likely that you would get your results if you went for a resource-heavy process. Time remaining. So I disagree with this one. Don't go for the least allocated. Go for the most. You can go for the lowest priority process. A lot of system OSs are using priority processes, and you can look for the ones with the lowest priorities. Well, there's lowest priorities, so least important. No one's going to miss them, right? So that one's probably the most palatable of the bunch, but it's probably going to be the one that is least effective. The lowest priority ones probably aren't using a whole lot of resources. Which is very true, because they're usually things that are collecting statistics and other fun stuff about your system usage and file system usage and stuff like that. So it's probably not going to help you much. Least total, like I said, I would go for the heaviest, not the least, but your author liked the least, so I put it up there. All of these are just chance, aren't they? Stochastic, probabilities. Not a good way to design and build a very advanced operating system on chance. So deadlock recovery is possible, it's just not good. Does anybody disagree with that? All right, this is the most response I've had so far. I'll go with it. Okay, so then we saw deadlock detection, we saw deadlock recovery. So let's take a look at deadlock avoidance. Okay, this is the one where we said we dynamically look at the resource request and determine if I should grant that request based upon whether or not it's going to get me into deadlock or not. In order to do that, I need to know something about future requests for resources. Which we'll come back and adjust that one here in just a minute. But how the algorithm works is that I'll run this algorithm and I'll say, this process is going to make a request for these resources. Then I'll say, don't start that process if its request for resources might lead into deadlock. It might lead into deadlock. And do not grant an incremental resource request to a process if that allocation also might lead into deadlock. Because while your process is running, other processes start running, and your future demands for resources at first, when you first started running, might have been okay, but other processes started running and grabbing some of those resources, and it may no longer be okay. So you'll have to check when you're starting your process, and you're going to have to check again when your process is making additional requests beyond its initial requests for these resources. Make sense? That's the high-level description of what this algorithm is trying to do. The classic algorithm that we'll study and most systems have implemented some variant of this is the Banker's algorithm. Okay, and what it does is it's going to have the state of the system's current allocation of resources to processes, similar but not the same as what you saw in detection. And it's going to run a safety algorithm. So it has an algorithm within an algorithm. So Banker's algorithm includes a safety algorithm where it says this request will be granted if there is at least one sequence of processes requesting resources that does not result in deadlock. In other words, I have at least one resource, one resource that I can give to a process that, given the rest of the resources it wants, it can go to completion and thereby freeing up resources. Okay? An unsafe state is I make this request for this resource and there are no such paths that exist. In that point, I do not grant this process's request. I do not grant this process's request at this time. I will send it to the end, usually to the end, but sometimes operating systems will put it in the middle of the ready queue and come back after some processes have run and released. Okay? So the safety algorithm, we're looking for at least one path. There may be more, but it's looking for at least one path that a process can run to completion before it'll grant the request, before it declares it safe, and the algorithm allows this process to be granted its request for this resource. Okay? So, a little slightly different. Okay? I have my claim matrix. I have my current allocation matrix. And then I have my claim minus allocation matrix over here. And similar before, I have a resource vector. This is how many of each of these types of resources I have in here. Working with larger numbers now. And I have how many are currently available in the system. Claim. This is the situation where we need to be clairvoyant about this process. How many of each type of resource is this process going to request at any given time? At most, over its life. This is how many of each type of resource each process is going to claim at most of during runtime. Okay? That's claim. And it's static. Well, it's sort of static. It's coming and going with processes, but I'm not going to update this table while I'm running these algorithms. This is when the process is loaded. The compiler knows in advance how many of each type of resource this process is going to need, and it's going to fill in this, and the loader is then gonna read that information and fill in this table when it loads the process into memory, okay? So that's where we get claim from, our good friend the compiler. Allocation, just like the allocation we saw in the previous one, and we're gonna update C minus A just as this equation states. C minus A equals there. See errors here, right? Should be correct. And then available and resource, just like we saw before. How many total and how many currently are available. So this is, we'll say this is our initial state. The system's obviously been running, right? Because I have 4 processes already in here, and they already have some things, some resources allocated to them, right? So we call this the initial state, but it's the initial state for the purposes of our study here. Yes?
Like in the real world situation, would this be loaded with every process that's currently running, or like I guess in like OS X or like Windows 10 or something like that?
You'll actually have a collection of these, because this is a family of resources that are sharing these resource vectors. So most operating systems today have separate ones laying around for these different clusters of processes. Some systems do have one giant set of tables and arrays. Some have index sets. Okay. So in this case here, P2 rest completion kind of tells us that P2 must have made a request, right? What if, or anybody makes a request, is there a process that can safely run to conclusion? Okay? So before granting, we don't care. It wasn't P2. It could have been P1. It could have been any process here. Made a request for additional resources. And what the safety operator will say, because first we're going to have to make sure we have these, whatever request is for that process before we even run the bankers, but we've already done that. Okay, so now bankers is going to run. So what it says, a process makes a request for a resource. Is there a path? Now, as you saw in slide 2, we said, oh, process 2 was declared safe by the bankers algorithm. So since we did that, let's see if we can understand what that means. Okay, currently, process 2 holds 6, 1, and 2. Its C minus A says all it needs is one more 3, right? We look inside of the available vector and we see, I do have a 3. So I have a path that exists. So I can grant this process a request, it runs to completion, and then it returns all of its resources into available vector. So after I run P2 to completion, I then take 6, 1, and 3 to make this 6, 2, and 4, right? Because it can run to completion. So I have 6, 2, and 4 at that point. Oh, 2 plus 1, okay. 6, 2, and 3 is what I would have in there because I'm just trying to add 1 and 1 to 1, 6, and 3. 6. No, it was 3. I was right. That should have been a 4. Stick to my guns. That should have been a 4 because that was a 3, and it had 1 in there. Okay. Now let's look at the process 1. We kind of jumped over that one because we looked ahead a slide, right? If our logic needs to be the same, right? We're not going to just randomly pick in our process and say, oh, let's try you, then randomly select another one. We're going to have some logic for like just going down the table and this order or that order, I don't care which order, just as so I'm consistent.
You're giving process 2 an additional 1, then the available vector would be 0, 1, 0, right?
Right.
So then when you put it back in, it would be 6, 2, 3.
6, 2, 4.
Because you should add
Because
the
you're
allocation.
Oh, I added this one instead of this one, that's
Yeah.
right. This is the one we're adding.
Yes.
6, 1, 2, so that's why it's 6, 2, 3. Thank you. So now let's look at process 1, because we're probably going to do that, we're gonna build logic, right? So we're either gonna go from first to last or from last to first, right, in most cases. So let's look what happened when we tried process 1. I have 1, 2, and 1, 3 available. Process 1 currently holds 1, 0, 0. Process 1 will need, over its life, 2 more 1s, 2 2s, and 2 3s. Do I have that available? No. That's why we skipped over process 1. But then that's the same question with 613. It's currently holding 612. Should be going from here, darn it. That's why we have a C minus A matrix, folks, so we don't have to keep doing this over and over again. So here we have 222, so we want to skip over that. 001, you said that could happen. 103, no. 420, no. So in this case, we happen to only have one solution, but that's not always the case. And all we're concerned about is there one? Any one? Don't care. As long as there's one, then I can grant this process's request. And as processes complete, they start turning in more resources, making it possible now for some of these processes like 4, which needs 420, to be able to now run to completion. See that? Yeah.
Does it go, the first one to find that it can take, it'll take?
Yeah, it'll let it run to completion. And then it has to continue through all processes in this group. All processes in this group need to be able to run to completion. If they cannot, then this is not safe. So even though I found one that I can release, catch and release or whatever, that's not the end of the safety algorithm. It's got to run through all the processes in this collection, in this set. And it turns out in this case, we have at least one path where all can run to completion. So we declare this safe and allow that request to proceed. The reason why we added that additional matrix is because we're running this over a number of processes, which means I don't want to do this same math over and over and over and over again, right? You just want to calculate it once, and then just reuse it, right? Okay. Questions on safe state? Yes?
So how do you, I'm confused on, how do you need to plug the numbers on the resource vector and the available vector, R and D?
Okay, so when the operating system starts up, it knows how many of each of these kinds of resources it has. And it will populate this array with those numbers when it starts up. Of course, now today with plug-and-play devices, it will update this every time one is inserted or taken away.
Okay, but how does R1 comes with a, right?
R1, that's how many was in this operating system when it started or has been added as people plug things in.
Okay.
And decremented as things are taken away, right? So that's how many of these are in the system, and that's managed by the OS itself. Other questions? Yeah.
Do systems really have all of these, or is this just for learning purposes, having all of these matrices?
Well, there are ways to optimize these implementations so that they're not full matrices as you see them. We can use bitwise sets to represent these. Yeah.
I know it's not really within the scope of this course, but if you have multiple CPUs, does each CPU have have their own, how would multiple CPUs share a particular resource? Or are they independent at that point?
So at that point, you're working with a shared memory space that all of the cores are using.
Gotcha.
Although there's some resources that are unique to each core that would have their own chains. Other questions on safe? Well, just like good code, you make it work on good conditions first. And then you really test it by things that make it break, right? You do error boundary checking and stuff like that, right, in your code? I mean, that's just what everybody does in their sleep, right? I thought so. So we want to look at what happens if there is an unsafe condition in our system here. Okay, so we have a slightly different initial state here. We still have 936, and we still have processes that mostly use these. Our current allocation right now is 112, and this is what our current allocation and our C-A matrices look like at this point. Okay? So the question to the crowd here is this an unsafe state? And if so, what do we do about it? Well, we know how to determine if it's safe, right? So let's do that, okay? P1, start with P1 here. P1 has 100 here, it needs 222. Is that possible? No. P2 currently has 511, it needs 102. Is that possible? Yes. Hold that thought a minute. P3 has 211. I know your algorithm at this point would have stopped, right? But I just want to fast forward here for a second. P3 211 needs 103. Is that possible? No, not given this current state. 002 needs 420. Is that possible? No. So we're really dependent upon P2 being able to run to completion and turning in resources, right? That 5 there looks pretty big to me. So yeah, let's go ahead and say, all right, I can let 511 run to completion, and it will turn in its currently held resources, as somebody clarified here, and turn them in. So this should look like 623, yeah? What happened here? P1 requests. Oh, so now we're going to do an incremental. Sorry, I got ahead of myself. I was going to run down to completion, but this is an incremental request. So P1 in this scenario wants one each of R1 and R3. Okay, so R1, R3, P1, that's within its C-A matrix. And we don't have an R1 to give it, do we? But that's not what the Baker's algorithm says. The Baker's algorithm says, is there any path? Right? And that's when we said, oh, wait, it needs 121, not available, 102. Ooh, that's not available. 103, that's not available. 420, that's not available. So in this scenario here, none of them can be granted your request, right? So did I declare this unsafe? If I declare this unsafe, that says I do not approve this request. This process will then go to the end of the ready queue, come back later and try again. Questions? So we've seen safe, and we've seen an incremental request that was unsafe.
What's the difference there with incremental? What does that mean?
Because I pulled out process one, and process one got its 2 resources, and now I'm looking to see if there's a safe state. If I grant process one this request, 1 and 1, one of 1 and 1 of 3, then my available would look like this. I then test to see if I have a path to success. I do not. So I granted that request to P1 and then ran my safety algorithm. And it said unsafe. So I told P1 it's going to have to wait. Yes?
Why doesn't it just run through its process and then return the resources?
It's not going to be able to run to completion. I granted it 1 and 1, but it still needs 1, 2, and 1. So it's not going to be able to run to completion. There's another process? No, no, no. So I can't grant that request. Anybody not see that? Okay. Good test material here. Absolutely. So the Banker's algorithm is what class of algorithm?
Avoidance. Avoidance.
Focus.
Avoidance? We all agree on avoidance? Yeah, okay, we'll call it avoidance. Okay, so here's what some pseudocode would look like to implement this. Pretty straightforward. As you can see, we have our resource and available vectors, our claim and alloc matrices. And I'm gonna go get my allocated and my claims. Pretty easy to read this one. Just another way to describe what we were just talking about. So that's just another way for you to help understand the SAFE algorithm as part of the overall Banker's algorithm. Right? So this is another way you can read through it and understand the logic. Okay, summarizing, deadlock avoidance. We have to know the maximum number of resources in advance. We'll have to task the compiler to calculate that or determine that in advance when it's compiling your code. Processes that are being considered, they're all, of course, independent. They're all not synchronized with each other, just like we do in true multi-programming operating systems. We have some fixed number of resources. It's known at OS startup time, unless we have some devices, some resources we add, in which case the operating system will update those tables. And no process may exit while holding any resources. It's worth saying that again because sometimes we forget. As part of the exit routine, right? Part of going from the zombie state to non-existent is turning in all your resources, right? So that, it's assumed you remember that stuff, but it's important to remember that's why this algorithm can work, is because we always know how many resources are being held, which means that processes are forced to turn in those resources before they may exit zombie. Make sense? With me so far? Yes. Okay, good, excellent. All right, deadlock prevention. So now we want to look at not just avoidance, we want to look at preventing deadlocks. Okay, so this particular class of algorithm works in the following way, okay? It's going to look at our 4 requirements for deadlock exists, right? Mutual exclusion, hold and wait, no preemption, circular wait. Exists means that deadlock exists, which is what we're attacking. So we have to go after any 4 of those, take any one of those away, and we can prevent deadlock from happening. All right, so how could we do this? Mutual exclusion. Mutual exclusion. Spool everything. What does that mean?
Put in a buffer. or
Buffer.
defer, yeah.
Yeah. How does that help?
Because you can pick and choose, or you're gonna run things at the very front, and the things in the back will, like the resources will be deallocated generally by the time, well, you're hoping by the time you get back around.
Right. Yes. Hold and wait. Hey, let's just give, I'm sorry, I meant to say, okay, so that's how you can implement it. What's the downside to this?
Space.
Space. Right? Do we have any data integrity issues here?
What, a spool?
Yeah.
I don't think so.
No? That's good? You're just spending a lot of time and a lot of memory spooling things around, yes. Hold and wait. Well, we can just give every process all the resources, max number of resources when we start up that process. That's pretty simple to do, isn't it? Because the compiler's already telling us how many resources the process is going to need. Is it efficient? Are we going to be able to allow as many processes to run at the same time? No. We'll be very limited on the number of processes, in fact, that we can create and have running in a hold and wait scenario where we're giving all processes, all resources, initial condition until it terminates. Right? So yeah, that'll work. I won't have deadlock. I'm just not very efficient. No preemption. How can we attack that? Just take the resources away. Right? Just go grab it. Oh, I need it.
Guess even safe.
That's
That's really risky.
It's really risky, right? Because just like we talked about earlier, right? If I take a resource away and I give it from your process to your process, suddenly he has all the bytes in your buffer. And you go to use your resource because you didn't know it was taken away, you could crash. Not so good. But you're not going to deadlock. You just cause another problem. Circular wait. Oh, this is a fun one. We'll just simply order all of our resources numerically, and that'll take care of our problem, right?
It'll take forever.
It'll take forever. Yes.
You can log in and have fun.
You trying to tell me that deadlock prevention is possible, just not a good solution? It's kind of like recovering from deadlock, huh? There's a bunch of solutions there. But you were too picky. You didn't like any of them. Tough crowd. All right, so summary table for you, which I would suggest is a great study guide item. Summarizes each of the different approaches, advantages, disadvantages. In the case of prevention, we have several schemes. We talk about those here as well. So I would encourage you to just go ahead and take that, use that as part of your study aid collection as you're looking through this chapter and the study guide and preparing for the exam on Wednesday. Any questions? Okay, well that's it for deadlocks. So let's go ahead and take a short break, mostly because I need to get a drink of water here. And